Hello all. I'm still in the cabin in the woods, and today I went to the sea for the first time in 2 years, and I swam a little bit, and I feel really rejuvenated. I feel like I'm 30 years younger or something like that. So I'm really excited to film this video. Okay, it's a Unit 3 paper. So this is the practical skills in Physics 1. So this is kind of like the baby practical skills in physics, because there is also Unit 6, which is practical skills in Physics 2, which is a little bit more advanced, but not as advanced as you would think. So this one is from May 2025. Okay, and I'm gonna say a few things before we start that I always, these are the same things I always say for strategy before each past paper video. But okay, so for this one, you have 80 minutes, okay? But there are 50 marks, okay? So if you recall in other past videos, I say that you should spend about a minute per mark. So if a question awards 20 marks, it should take you 20 minutes. Here there is a little bit of wiggle room. So if it takes you 25 minutes, it's fine. But guys, try to stay on time to score maximum marks, okay? So that's the first thing. The second thing that applies to every test from kindergarten to all the way to graduate school, okay? Half the answer is in the question. What does that mean? If you read the question thoroughly and if you understand what's going on and what they are asking you to actually solve, then you have already solved half the problem, because your mind is going to be directed in the correct direction, okay, for the solution. And that's the second thing I wanted to say. The third thing is to go over the questions that you know how to solve immediately, meaning that if there is a question in which you don't even know how to start, skip it, okay? And work on the problems that you already know, so you build confidence and momentum, and you can return to the questions that you don't know how to solve in the end, okay? And for the questions that you don't know how to solve, you can go to the back of your paper and read the formula sheets and all the constants that they give you and the formulas, and maybe you will get inspiration about how to solve the actual problem. And I'm showing the formulas that they give you. And the last thing is, for example, let's take a look at this question. So it has a part A, a part B, as you can see, a part C, etc. So sometimes part A might not make too much sense to you, in which case you can actually, without replying or answering part A, you can skip it and jump to part B, read it, and then you might get inspiration about what part A is actually asking you, because sometimes in part B, they say things that are related to part A, okay? These are all the things I wanted to say. So let's jump into the actual test and start with question 1, okay? So question 1 is asking, a student made measurements on the solid metal prism shown. Question A, the student used the balance to determine the mass of the metal prism. The reading on the balance is shown below. So we see 135 grams. State the resolution of the balance. Okay, so the resolution is the smallest deviation of the instrument that you use to take a measurement. Okay, and see here, the smallest resolution is really 1 gram. Okay, so 1 gram is, so the resolution is 1 gram, and we can also write here resolution is the smallest deviation of the instrument, okay? And also recall that half the smallest resolution of your instrument is the absolute uncertainty in the measurement, okay? Which is actually the second question. So part 2, determine the percentage uncertainty in this reading. So we can say that the absolute uncertainty in the measurement of mass is half the resolution. In case you have a series of measurements, it's the half range, okay? But here it's just a single measurement using the instrument. So half the resolution, which is 0.5 grams. And then the percentage uncertainty in the mass is equal to the absolute uncertainty in the mass over the mass itself times 100. So here we have 0. I'm going to write it down here, 0.5 over 135 times 100% gives us 0.37%. That's the answer. Okay, let's move on to part B. The student used vernier calipers to determine the lengths A, B, and C. Explain question 1. Explain one technique he should use to determine accurate values for these lengths. So you can the student can take repeat measurements as usual. Sorry, let me try to fix my handwriting. So repeat measurements. Another thing they can do is to check. So no, before we say that, let's say that, okay, you take the repeat measurements and then you average the repeat measurements, okay, to minimize random error. Okay, so that's almost a complete answer, but since this is this channel has a purpose of teaching people things, okay, so the other thing is you can check the vernier calipers, for 0 error. Okay, and what does that mean? If you close the vernier calipers and you're measuring like 0.01 millimeters, for example, that's the 0 error. Okay, so you have to fix that. So when the vernier calipers are totally closed, okay, fully closed, then you should measure 0. Okay, so part 2, the student checked that the angle between the side of length A and the side of length B was a right angle. He did not have a set square or an instrument to measure the angle directly. Describe how he could use one other measurement and a calculation to check the angle. So here they are prompting you to say that, okay, he can measure the hypotenuse, okay, which is not C, by the way. The hypotenuse is let me use red. So that's the hypotenuse. Okay, so let me redraw it. Okay, so hypotenuse. Okay, hypotenuse. Okay, so they can measure that hypotenuse and check if if you take the square of the hypotenuse, it should be the sum of the square of A and B, right? So let's write it. Let's write things down. So measure the length of the hypotenuse. Use Pythagoras to check whether A squared plus B squared is equal to C squared. So if A squared plus B squared is equal to C squared, then the angle is a right angle, so 90 degrees. Okay, so that's the answer. We can move on to part 3. Determine the density in grams per cubic centimeters of the metal. And they give you the sides A, B, C, and the mass of the prism. Okay, so the volume is going to be A times B times C over 2. Okay, because we have half a parallelepiped. How do you call that? Parallelepiped, something like that. It's in Greek, it's parallelepipedo. Okay, so I always have trouble spelling it in English, so I hope you understand. Okay, so you take the volume of the parallelepiped, okay, and you divide it by 2. So ABC over 2. So 25.3 millimeters is 2.53 centimeters, and similarly 2.49 centimeters for B and 4.96 centimeters for C. So we have 2.53 times 2.49, times, not plus, excuse me, times 4.96 over 2. And this yields 15.62 cubic centimeters. Okay, Then the density is, of course, mass over volume. So 135 over 15.62, which yields 8.64 grams per cubic centimeter. Okay, now part 4. The percentage uncertainty in this calculated value of the density of the metal is 0.9%. The accepted value for the density of copper is 8.94 grams per cubic centimeter. Deduce whether the prism could be made of copper. Okay, so the percentage uncertainty in rho is equal to the absolute uncertainty in rho over rho. Okay, so here we need the absolute uncertainty in rho, which is rho times the percentage uncertainty in rho. I hope I'm not confusing you. So 0.9% times 8.64, which is what we measured. So this yields 0.08 grams per cubic centimeters as the absolute uncertainty. So the max rho is going to be rho plus the absolute uncertainty in rho. So 8.64 plus 0.08, which yields 8.72 grams per cubic centimeter, which is less than 8.94 grams per cubic centimeters, which is the density of copper. So not copper is our answer. Okay, and this was question 1. It awards 12 marks. Straightforward but long, and you have to think thoroughly, especially for the parts where you have to write your judgment about a question, meaning part B, question B. Okay, so let's move on to question 2. Okay, question 2. A student investigated the motion of a small sphere on a curved track using the apparatus shown. Question A. The student marked the track at the rest position of the sphere. The student then marked the track at the start position of the sphere. She used the meter rule to measure the horizontal distance d between the two marks on the track. Describe an accurate method to measure a single value of d. So you can clamp the meter rule, okay, in a position close to the track, okay, so it does not move during measurement. So it does not move during measurement. Okay, so that's the first step. The second step is to use a set square, okay, against the vertical stand. So you can probably clamp the ruler, for example. Let me show you visually. So here will be your ruler, and then you can use a set square to figure out that it's horizontal, okay? So use a set square against the vertical stand, okay, to check that the meter is horizontal. Okay, then make sure the zero of the meter rule lines up with the rest position of the mark. Okay, use a set square. So make sure the zero of the meter rule lines up with the rest position of the mark. So the zero should be here, in other words. Okay, so and then use a set square to measure the position at each mark to avoid parallax error. Okay, so use a set square to reassure, okay, the position at each mark to avoid parallax error. So it's a little bit involved, but I hope it makes sense. So you will use your set square to make sure that that's your start and that's your end. Okay, actually here is the start and here is the end. Okay, so this was question A. Let's move on. Part B, the student placed the sphere at the start position on the track. The student released the sphere. She used the stopwatch to measure the time t for the sphere to come to rest at the rest position. The student repeated the measurement several times and recorded the following data. Determine the mean value of t. So t average is the sum of all values divided by 4, which is the number of all the values measured, right? So we are adding everything up, divide by 4, we get 5.45 seconds. Okay, question 2, determine the percentage uncertainty in the mean value of t. So the absolute uncertainty in t is the half range. Okay, so the maximum value, minus the minimum value over 2, so 0.44 seconds. Okay, let me measure it again. So 0.44 seconds. And then the percentage uncertainty in t is the absolute uncertainty in t over the average time times 100. So 8.1%, which is quite large, I have to say. Okay, let's move on to part C. The student investigated how varying the distance d affected the mean time t. She recorded the following data. The student used the data to plot the graph, criticize the data recorded by the student. Okay, so first of all, you see that d is measured with various numbers of decimal points. So let's write that down. So d has a different number of decimal places, which is inconsistent. Okay, so only 4 sets of data are taken. So only 4 sets of data, which is not enough for a plot. Okay, no repeats. And in addition, there is a crazy data point. So this one, okay, so probably the mean time there should be 8.2. Okay, because it doesn't make sense, because we jump from 14.5 centimeters to 17 centimeters and the time jumps by however times, so 12 times more, is it 14 times more, so it's crazy. So that's an outlier. Data point at 17 centimeters is an outlier. So that's that. Okay, part D, the student suggested using a video camera to record the motion of the sphere. Explain how using a video recording could improve the measurement of t. So you can record the motion, okay, and play in slow motion, right, to see exactly when the sphere stops moving. Okay, so this removes the reaction time, okay, the reaction time error, let's say that, okay, that comes from starting and stopping a stopwatch. Okay, so time can be measured more accurately using video recording. Okay, and this was question 2, okay, a long question as well, but also straightforward, I would say. So let's move on to the next question. Okay, question 3. A student investigated the power output of a power supply using the circuit shown. Let me see the circuit, okay, and it has some internal resistance. That's the idea there. Okay, and we have a variable resistor, a voltmeter, and an ammeter. The power supply has an internal resistance. Before switching on the power supply, the student used an ohm meter to check that the variable resistor was set to the maximum resistance. He then measured corresponding values of current and potential difference for a range of resistances. Question I, explain why starting from the maximum resistance is safer than starting from the minimum resistance. Okay, so this goes back to, okay, current in general is voltage over resistance. Okay, so if R is high, current is low, right? So this is what we will write. So max R means minimum current. Okay, so this protects the components such as the ammeter, okay, from a large current that can damage them. Okay, question 2. Explain whether repeat readings are appropriate for this investigation. So, not really. I mean, I don't see why. So, repeats are not really needed. Okay, at a fixed resistance. Oops, okay. At a fixed resistance, I and V should stay essentially constant. Okay, so repeated readings will show little variation. Okay, so random error is small in this case. Random error is small. Okay, moving on. We see that pretty graph there. So B, the student used his results to plot a graph of the power output of the power supply against the resistance of the variable resistor. As shown, the power output is at its maximum value when the resistance of the variable resistor is equal to the internal resistance of the power supply. Determine the internal resistance of the power supply. So basically you have to find the maximum power output, so that point over there, I believe. So that's 2 ohms, so that's 1 ohm. So each deviation is 0.2, so 1.2, 0.4, 0.6, 0.8, and we see that our point there is let's see. So that's 1.6. Okay, so R is approximately 1.6 ohms. Okay, how do I know that each small deviation is 0.2? Because the large square is 2. Okay, so we have 2 over 10 very small deviations, so 0.2 ohms per deviation. Okay, so that's the trick there. Okay, part 2, determine the output potential difference of the power supply when the power output is a maximum. Okay, so power is V squared over R, right? So V is P times R, and we need to take the square root of that. Okay, so that's the square root of the power, which is okay, so each small deviation in the y direction is 0.1, because that's 1 watt over 10 gives us 0.1 watts per deviation. Okay, so we see that we have about 5.7, right? So 5.6, maybe 5.7, something like that. I used 5.7, so 5.6 is probably still fine. So 5.7 times 1.6 yields 3 volts, pretty much. All right, so let's move on. Part C, when the power output is at its maximum value, the overall efficiency, is 50%. Radio transmitters are used to transmit radio waves over a large area. The area connected to the radio transmitter has an equivalent resistance equal to the internal resistance of the transmitter. Suggest one advantage and one disadvantage of making the resistances equal for a radio transmitter. So the advantage is the maximum power we just saw. So matching the aerial, by the way, an aerial is an antenna pretty much, okay? So matching aerial R to internal R, okay, delivers maximum power to aerial. So this means strongest signal that can travel further. Okay, the disadvantage is heating, and you lose power. I mean, the efficiency is 50%. So disadvantage, since efficiency is 50% at max output, okay, half the energy is lost as heat in area. So it's wasteful energetically. Okay, this was question 3. We are ready to move on to question 4, which is the last question. Okay. Question 4, a student determined the speed of sound in air using the apparatus shown. It's a little bit complicated, but I mean, if you notice here, this is an empty cylinder, okay, and there is water, so sound waves are reflected off the water, and sound is produced in the cylinder, in the tube. Okay, so that's the idea. Okay, question A. The student used the meter rule to determine the distance L between the level of the water and the top of the transparent cylinder. Explain how to reduce a source of uncertainty in the measurement of L. So use a set square, okay, placed between the top of the cylinder and the meter rule, okay. So the reading is taken directly in line with your eye. So is taken in line with your eye. And I will need an extra space to write that this minimizes parallax error. So this minimizes parallax error. Okay. B. The student connected the loudspeaker to a signal generator. She set, the frequency f of the signal generator to its lowest value. The student gradually increased f until a standing wave was produced in the transparent cylinder. The sound from the cylinder was loudest at this value of f. Explain a technique the student could use to determine as accurately as possible when a standing wave is produced in the cylinder. So she can increase. So she can increase f slowly past the point of loudest sound. Okay. Record the f when this happens. Okay, and then she can decrease f back past f at loudest sound. Okay, and let's go back here and continue to write that you have to take the mean between the two values, okay, as judging the exact peak is hard. Okay, I hope this makes sense. So there is a knob, I guess, okay, that you can turn to the right and increase f until you go a little bit past the loudest sound. So record that, and then turn the knob back down to reduce f, go past the frequency of loudest sound, record that as well, and then take the mean. Okay, so I hope this makes sense. Let's move on. Part C, the student recorded the value of f for the first loud sound. She continued to increase f and recorded the next 5 values of f that also produced a loud sound. She gave each of these recorded values a number n. For the lowest frequency, n equals 1, and for the highest frequency, n is equal to 6. The student suggested that the relationship between f and n is given by the formula f is v over 2l times n plus k, where v is the speed of sound in air and k is a constant. Question I, explain how a graph of f against n can be used to determine the value of v. Okay, so f is v over 2l times n plus k. So this has the form y is equal to mx plus a constant, and you can see that m, the gradient is v over 2l, x is our n, and c is the y-intercept, so k. So we can write that gradient is going to be v over 2l, and k is going to be the y-intercept. So it's a classic y equals to mx plus c relationship, which is nicely plotted. You can infer the gradient and stuff like that. Okay, question 2. The student recorded the following data. So n goes from 1 to 6, as it was stated in the beginning, and f goes from 128 hertz to 1608 hertz. Okay, so this is a range of about 1600 hertz. So in our deviations in the y-axis, we will take deviations of 200 hertz, and you will see what I mean when I turn the page. Okay, let's do this. So let's use orange so it's more visible. So this is the frequency, okay? So this is the frequency in hertz. Let me raise this and do it at Excel style. So f in hertz, and then n. N has no units. N is a number, okay? So this is 1, 2, 3, oops. So we will use each square to denote an integer number. So 3, 4, 5, and 6, okay? And now for the frequency, as I said, we will make this the 200, okay? So that's the 0, then 400, so each large square is a jump of 200 in hertz, okay? So 800, 1000, 1200, 1400, 1600, and then 1800. Okay, I'm gonna show you the first data point, and then I'm gonna probably show you the final result. Okay, so the first data point for n equals 1, f is 128. So so 200. So every little square in the y direction is 20, an increment of 20 in hertz. So 128 should be, so that's 120, 130. So somewhere just there. Okay, actually, that's the first data point. Let's do the second as well. 445 hertz. So so that's 400. That's 500. So 420, 440, 460. So somewhere there is the second data point. And now I'm gonna show you the final result. Okay. Okay. So this is the final result. A really nice straight line can be passed from all these points. Okay. So let's do that. So let's start from up there and try to pass through all the points. So, okay, so there. That's our very pretty line. Okay, I kind of like it. I don't know. So usually, I mean, it doesn't come out as nicely. So okay, I'm gonna extend this so the y-intercept is visible for later. All right. Okay, so this is our plot. Let's move on to the next question. Okay, question 3, determine the value of v from the graph. So the gradient is delta f over delta n, and you can choose any 2 points on the graph. In my case, this is a trick that a past student, a former student, okay, that's the correct way to to put this. So a former student figured out that if given that the 2 points are on the graph, so the highest value and the lowest value, I mean, if you use those points, you get something close to what Edexcel asks you to find. Okay, so, oops. So wait, yeah, something like that. So this is your delta f, and this is your delta n. I hope things make sense. So, but what we are really doing is that we take the minimum and the maximum from the graph. Sorry, from the table, given that they are on the straight line fit. Okay, I hope this makes sense. So 1608 minus 128 over 6 minus 1 yields 296, and the units are seconds to the minus 1, also known as hertz in this case, but anyway, okay. But we also know that the gradient is v over 2L, so v is 2L times the gradient, so 2 times 0.595 times 296 meters per second, so 352.24 meters per second. The speed of sound, correct me if I'm wrong, but it's usually 340 meters per second, I think. But this is off the top of my head. I didn't check anything, so check for yourselves. But this looks good to me. Okay, what else? This is it for part 3. Part 4. Part 4, the student suggested that the magnitude of k is half the magnitude of the gradient. Determine whether the student's suggestion could be correct. Okay, so in this plot, the 0 of our axis is the 0 of the n and the 0 of the f. So in this case, you can use the y-intercept. I guess that's the easiest way to do it. So from the y-intercept, so that's minus 100, and then 20 minus 140. It seems so, right? So k is about minus 140 seconds to the minus 1. Okay, so 2k, if we take the absolute value, the magnitude, is 280 seconds to the minus 1, which is less than 296 seconds to the minus 1. So student is wrong, but not too wrong. I mean, it's kind of close, but that's fine. So student is wrong. In case your axis does not start at 0, okay, in which case finding the y-intercept can be complicated. Another way to find the y-intercept is okay, so that's the first way, I guess. So let's name it like that. The second way is to use a data point and the equation. So the equation is f is the gradient times n plus k. So k is f minus the gradient times n. You can choose, for example, the pair of values 1608 and 6, right? And if you plug in there, you will find that k, and this pair is this pair over here, okay? So this one. Okay, so if you plug in, you find 1608 minus 296, which is what we calculated earlier, times 6. In this case, we find minus 168, in which case 2k is 336 seconds to the minus 1, which is larger than 296 seconds to the minus 1. So again, the student is wrong, but again, not too wrong. I mean, it's kind of close. So anyway, this was unit 3 from, what was it, May, I think, let me check. Yes, May of 2025. I hope these videos are useful. Not a lot of people are watching them because it's the summertime, which alerted me a little bit. So I'm trying to think and create general physics videos related to other topics. So I want to move a little bit away from A-level physics in terms of content, but I will keep uploading A-level content because people enjoy these videos and they find them useful. But I also need to make this channel viable. So, okay, I mean, I understand students are not gonna watch these videos outside the school season or the exam season, etc. But I also have to make a living, guys. So I will try to create many types of content, and so that the viewership of the channel grows. So anyway, because it really helps the channel, please like, subscribe, send these videos to your friends that might find it useful. Thanks for watching. Thanks to the ones who who write comments and feedback for my channel. It's really helpful. So I'm gonna see you in the next video, guys. Bye.